All right, so here we're going to actually get into geometric proofs. So far we've kind of just talked about each of these as a definition, but some of them are actually postulates or theorems that we needed to build up to prove. We are going to take these, everything that we've talked about, as an accepted definition or postulate. Those two words are going to be kind of interchangeable for us, but really we've just talked about them in a sense of problem solving rather than actually using them as reasons to justify what we're doing in problem solving. So before we can actually jump into this, so these are all things that we've already talked about. These are all the angle relationships we talked about in the last video. But before we can actually use any of those, we really have to talk about the language of logic. So when I talk about the language of logic, really what I mean is airtight logic that takes us from a given statement to a proven statement. So to do that, we are going to use something that's called a conditional statement, which is really just two statements. One is the hypothesis, where we start out with claiming something, and the other is the conclusion that follows from that hypothesis. So we're going to represent that with a P and the Q. P is the hypothesis, Q is the conclusion. If P, then Q. If P is true, it implies that Q is also true. And this is exactly how we're going to write that P with the arrow leading to Q. So P, then Q. So that's really just two statements where one follows the other. Each of these three is basically just a different version of that. So we have a statement followed by another statement. The converse is flipping those two around. Q, then P. All right, so actually let's go to an example of this because I think that might make it a little bit more concrete. Let's say if Lucy is a dog, then Lucy is a mammal. So first off, that is a true statement. If Lucy's a dog, then Lucy is also considered a mammal. So the conditional statement there is true. The converse of that is not true. We can't flip this around. We can't say if Lucy's a mammal, then Lucy's a dog. There are other types of mammals that are not a subset of the group of dogs. The inverse of this would be negating P and negating Q, and the way we're going to write that is with a tilde symbol, that little squiggly. It's still in the same order, not P, then not Q. Which again, in this case, that's not true. If I were to say, if Lucy is not a dog, then Lucy is not a mammal. That's again not true since there are other types of mammals that are not included in the subset of dogs. The contrapositive is the converse of the inverse, or we're actually just doing both of these changes. We're going to flip this around, and we're going to negate both statements. I'm actually going to write that one. If Lucy, if Lucy is not a mammal, then Lucy's not a dog. And that one's true. Actually, if the conditional statement is true, then the contrapositive will also be true. If Lucy is not a mammal, then she cannot be a dog. That is a true logical statement. So you can see that just because the conditional statement is true doesn't necessarily mean that these are true. But in a biconditional statement, if one of these is true, then they're all true. So a biconditional statement is an if and only if statement. I might abbreviate that as IFF. And really what that's implying is that it's by definition. So let's say if a number is even, then the number is divisible by 2. Which is pretty much just the definition of an even number, that it is divisible by 2. We can rearrange this and negate it however we want, really, and it will still be true. So that's the straightforward conditional statement. The converse would be if a number is divisible by 2, then it's even. That's also true. We could negate both of these. If a number is not even, then it is not divisible by 2. That's also true. Or we can flip these two statements around then. If a number is not divisible by 2, then the number is not even. So a biconditional statement is a two-way arrow going back and forth between P and Q. It's basically saying that the conditional and the converse are both true, so all 4 of these types of statements are true. Normally we'd have about 2 weeks to cover logic as a topic. Unfortunately, we really just don't have the time for that, so this is just a little crash course on how I'm going to be using these words. It's really just important that you'll understand the implications of a conditional statement, an if-then statement, and how each of these words could be used surrounding that if-then statement.